All right, trigonometric limits. Like I said, trig functions create some issues at times, so we're gonna get it gets its own special section. The first thing we're gonna look at is what's called the squeeze theorem. It's like dropping a bomb on limits. It's like boom, and it's cool. All right. Okay, the squeeze theorem, the concept of it, says if I have some function, let's call it L of x, I guess that's what your book calls it. And then I have some function U of x. And then I have an f of x between it. Something of that nature. So what we have is L of x. Let's say U of x is less than or equal to what we'll call f of x, which is less than or equal to L of x. Okay, there's kind of a hierarchy there. Yeah. You want me to rewrite it? Okay, that's what it says. So we know that their f of x is always between the two. The limit, and we also have to know that the limit as x approaches any c value of L of x equals the limit of U of x. It's just some value, we don't know what it is. This is a generalization. So what's the limit as x approaches c of f of x going to be? If we have u coming in, L coming in, what's f going to be? If it's always between them. Yep, then.
So all of the equations you're writing are true?
Yeah, so this is true. Okay, so we could start it with an if you want.
Okay.
F is between U and L. And that's true. We know that this is true. Little nursery over there. So basically we're taking these two functions, squeezing them together so that they meet at a point, and f has to be between them or equal to them, so it has to go through that point as well. It's the concept. Do you understand the concept of squeezing together?
Yep.
Coming to a point?
Yep.
We're trapping it. It's like a f of x sandwich, right? Okay. We can use this to show that's true. Are you guys okay? Are you sure? Stop it! I know somebody like that. Woo! I win. I wasn't meaning that to you, but okay. Okay. Yeah, this is an example. The
Have you ever encountered function with
x to the power of x?
no, like function f of x, but x of x?
You could, but that would be stupid.
Yeah.
Here's what we're going to do. We're going to trap it between those two functions because the original looks like this. It's kind of funky.
So we can choose random equations?
No, I'll show you how to build them. I'm just trying to give you the idea of what we're doing here. Okay, so that's what that function looks like. You see how those two functions kind of trap it in and squeeze it? So the limit's going to be 0 graphically, right? Algebraically, what do we know about sine? What two y values does it occur between? Always. Yeah, 1 and -1. So, like so. So this is how we're going to build our trap. So we know that this is true. That's the definition of absolute value. A definition of absolute value, and this is now our original function has an x in it, right?
Yeah.
So we need to put that in. Yeah, so this is the maximum and minimum of sine. And then that definition of absolute value is what we did here. Okay, now to build this, we need to multiply by so what we end up with is that right there. Now reuse the definition of absolute value. And what have we just done? We have negative absolute value of x, which is actually blue. I'll put blue up here. And then we have the absolute value of x, which is the green one. And now we have our function, which is the purple one. Our last step what is the limit as x approaches 0 of negative absolute value of x? Plug it in, plug it in. 0. And the limit as x approaches 0 of absolute value of x? 0. Okay, we'll point out that they're equal. By the squeeze theorem, the limit as x approaches 0 of x sine 1 over x is 0.
Oh my god.
Are you being sarcastic?
Yeah, I don't even know what you did. I'm just like,
I just wrote a bunch of stuff down. That's bad sign.
and I just copied it.
Okay, where did you get lost?
Oh, we're not talking about it. Okay.
Okay, do you understand where I got that?
Yeah. Yeah.
Everybody?
Wait.
Sine is between -1 and 1.
Yeah, that makes sense. The function's
Because it's just the sine wave, right? Between -1 and 1. Okay, I use the definition of absolute value
Where'd you get absolute value?
because it's between -1 and 1. Remember, absolute value is the distance from 0. Each of those -1 and 1 is 1 unit from 0, right?
Then what if it were an equation where it was a sine function that had like it's 2 sine x? Then would it be 2? That's about 2?
Yep,
Oh. Okay.
yep. You look at the amplitude there. Okay, then I had to multiply by absolute value of x because I'm building this. That's why I brought the x in. Then I undid the definition of absolute value. The bars in the middle disappear, but the bars on the outside do not. Okay. So I have the middle is my original function, that's what I want. And then these are my brackets, my squeeze, that's these two, we're squeezing in on it.
Okay.
Then we have to show that the limit of each of those is 0. You can see that graphically, right? Goes to 0, goes to 0. So we show each of those limits is the same. Then we know the limit of this function between them is also 0. You have to show that. I'm going to let you do another one when we're done with the lesson, because I have 2 more things to show you. No, I changed that plan earlier. Okay, 2 important trig limits. These are ones you need to memorize. You guys are comfortable using theta, I hope? These are theorems. For these, that's all you're going to write down. So no. Yes. Those are just facts that you need to know. We're going to use them right now, though.
Okay, we're going to use this theorem up here to evaluate this function. It's kind of a little bit of algebra because you can't just substitute straight in. The idea here is for us to create theta and theta here. So let me show you how to do that. We're going to take the function and we're going to multiply it top and bottom by 4. This is where you do your trick. We're going to take 4h and substitute theta for it. So we get 4 sine theta over theta. Taking that and put it in here. Does that look more familiar? We can use our theorem now. But we have to be careful. If I changed h to theta, I have to change it in the limit. So now it's the limit as theta approaches what? Okay, yeah, h was 0, so 0 equals theta. So we've, okay. So theta is going to be approaching 0 as well. Okay, so be careful that you have to change that h to a theta and you make it happen accurately. Most of the time it will transfer straight over to a 0, which is what you want, but you have to be careful because sometimes we like to try to trick you. We're tricksters like that, you know? All right, so what's that limit going to be? Yeah. Bam. Yeah, that would be great. Let's confuse you even more. Okay, those are the two examples, and I want to point out to you one more theorem. That's a direct result of the squeeze theorem. There's a picture in your book. basically, y equals 1. Just sketch it out for you real quick. And then there's cosine, right? Sine theta. Whoop. Old. I do that once in a while. So you have the top function is 1. The bottom is cosine. Between them is sine theta over theta. Looks kind of like this.
That's the line that yeah. That's speed. My recipe was speed with 2 on the sides, and sides through the main. Yeah.
Okay, that's a lot of work. Let me see if I can narrow it down a little bit. For now, start with
What is the equation for the line that you have in the middle?
that's sine theta over theta.
Oh.
This is a picture of that. Start with number 7. No? I want you in class right now to start with 7 because it's a squeeze theorem problem like you asked me for another example. I'm looking. Just start with number 7.